Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Baptiste Joseph Fourier's The Analytical Theory of Heat, published in 1822, represents a monumental achievement in mathematical physics. It introduced groundbreaking techniques for analyzing heat flow and established mathematical tools that are now central to a plethora of scientific disciplines. To appreciate its significance, one must consider both the intellectual climate preceding its publication and the profound consequences that followed. Prior to Fourier's work, the mathematical description of heat was rudimentary, while scientists such as Isaac Newton had formulated empirical laws of cooling. A comprehensive theory capable of predicting temperature distributions in complex geometries remained elusive. The existing approaches, often relying on intuitive arguments and limited experimental data, lacked the rigor and generality needed to tackle practical problems. Furthermore, a debate raged regarding the nature of heat itself, with some arguing for its particulate nature, the caloric theory, and others favouring a wave interpretation. Fourier's analytical theory provided a decisive break from these earlier efforts. The work's central thesis revolves around the idea that any arbitrary function, representing the initial temperature distribution in a body, could be expressed as an infinite sum of trigonometric functions, now known as a Fourier series. This assertion, audacious for its time, allowed Fourier to transform complex heat conduction problems into simpler algebraic equations. Specifically, Fourier considered the heat equation, a partial differential equation describing how temperature changes over time and space. In one dimension, this equation can be written as the partial derivative of temperature with respect to time equals alpha times the second partial derivative of temperature with respect to position, where alpha represents the thermal diffusivity of the material. Fourier's genius lay in recognizing that by expressing both the initial temperature distribution and the solution to the heat equation as Fourier series, he could reduce the partial differential equation to an infinite set of ordinary differential equations, each corresponding to a single term in the series. These equations could then be solved independently, and their solutions recombined to yield the complete temperature profile. The analytical theory meticulously develops these ideas, providing detailed derivations and numerous examples. Fourier explored heat conduction in various geometries, including infinite plates, cylinders, and spheres. He derived expressions for the temperature distribution under different boundary conditions, such as constant temperature, insulated surfaces, and radiative heat loss. His work demonstrated the power of mathematical analysis in solving practical engineering problems, from determining the optimal thickness of insulation to predicting the cooling rate of industrial components. The initial reception of Fourier's work was, however, far from universally enthusiastic. Prominent mathematicians, including Joseph-Louis Lagrange, expressed skepticism regarding the generality of Fourier's claim that any function could be represented by a Fourier series. These critics questioned the convergence of the series and raised concerns about the validity of the results for discontinuous functions. Indeed, the rigorous proof of the convergence of Fourier series under fairly general conditions did not appear until later in the 19th century. Despite these initial reservations, the analytical theory soon gained recognition for its practical utility and mathematical elegance. Physicists and engineers rapidly adopted Fourier's methods, applying them to a wide variety of problems beyond heat conduction. His techniques proved invaluable in analyzing wave phenomena, such as sound propagation, light diffraction, and fluid dynamics. The concept of frequency domain analysis, inherent in Fourier's work, revolutionized signal processing and forms the bedrock of modern communication technologies. One particularly striking application of Fourier's work involved the analysis of musical instruments. Hermann von Helmholtz, in his seminal work on the sensations of tone as a physiological basis for the theory of music, used Fourier analysis to decompose complex musical tones into their constituent frequencies, revealing the harmonic structure of different instruments. This analysis not only elucidated the physical basis of timbre, but also provided insights into the physiological mechanisms of hearing. The influence of Fourier's ideas extends far beyond the realm of physics and engineering. In mathematics, the study of Fourier series and Fourier transforms has blossomed into a vast and active area of research, with connections to harmonic analysis, functional analysis, and number theory. The concept of representing functions as sums of simpler basis functions has become a cornerstone of mathematical modeling, permeating fields ranging from image processing to financial mathematics. The Fourier transform, a generalization of the Fourier series to non-periodic functions, has become an indispensable tool in numerous scientific disciplines. In quantum mechanics, the Fourier transform provides a fundamental link between the position and momentum representations of a quantum state. In medical imaging, techniques such as magnetic resonance imaging (MRI) rely heavily on Fourier transforms to reconstruct images from raw data. In cosmology, Fourier analysis is used to study the distribution of galaxies and to extract information about the early universe from the cosmic microwave background. Consider, for example, the application of Fourier transforms in image processing. An image can be represented as a two-dimensional array of pixel intensities. By applying a two-dimensional Fourier transform to this array, one obtains a representation of the image in the frequency domain, where each point corresponds to a particular spatial frequency. This representation allows for the easy manipulation of the image, such as noise reduction, edge detection, and image compression. Filters can be designed to selectively attenuate or amplify certain frequencies, thereby enhancing or suppressing specific features in the image. It is perhaps a testament to the brilliance of Fourier's work that his techniques continue to find new applications and inspire new theoretical developments even today, 2 centuries after its original publication. From the design of efficient algorithms for data compression to the development of novel methods for medical diagnosis, the legacy of the analytical theory of heat persists as a cornerstone of modern science and technology. The impact of Fourier's work is further amplified by its role in shaping the development of numerical methods. The finite element method, a widely used technique for solving partial differential equations, relies heavily on the concept of representing solutions as linear combinations of basis functions. Fourier's work provided an early example of this approach, demonstrating the power of approximating solutions using a finite number of terms in a series expansion. This paved the way for the development of more sophisticated numerical methods that are now essential for simulating complex physical phenomena. Moreover, the analytical theory of heat played a crucial role in the development of the concept of orthogonality. The trigonometric functions used in Fourier's series form an orthogonal set, meaning that the integral of the product of any two distinct functions over a given interval is 0. This property allows for the easy calculation of the coefficients in the Fourier series, as each coefficient can be determined independently of the others. The concept of orthogonality has since been generalized to other sets of functions and has become a fundamental tool in linear algebra and functional analysis. The study of orthogonal polynomials, such as Legendre polynomials and Hermite polynomials, owes much to Fourier's pioneering work. These polynomials arise as solutions to various differential equations and play a crucial role in many areas of physics and engineering. For example, Legendre polynomials are used to describe the angular dependence of the electric potential around a charged object, while Hermite polynomials are used to describe the energy levels of a quantum harmonic oscillator. The orthogonality properties of these polynomials allow for the efficient calculation of various physical quantities, such as the energy spectrum of a quantum system. Looking back, it is easy to appreciate the magnitude of Fourier's achievement. The analytical theory of heat was far more than a mere treatise on heat conduction. It established a new paradigm for mathematical modeling, demonstrating the power of representing complex phenomena as superpositions of simpler components. It introduced mathematical tools that are now indispensable in a plethora of scientific disciplines, from physics and engineering to mathematics and computer science. Fourier's work not only solved practical problems but also opened up new avenues of theoretical inquiry, shaping the course of scientific progress for generations to come. It is also worth noting that Fourier's work had a significant impact on the development of mathematical analysis in general. His insistence on rigor and clarity helped to raise the standards of mathematical proof and argumentation. His work also stimulated the development of new mathematical techniques, such as the theory of distributions, which provides a rigorous framework for dealing with discontinuous functions and other singularities. In conclusion, the analytical theory of heat stands as a testament to the power of mathematical thinking in solving real-world problems. Baptiste Joseph Fourier's genius lay not only in his ability to develop new mathematical techniques, but also in his vision of how these techniques could be applied to understand and control the physical world. His work has had a profound and lasting impact on science and technology, shaping the world we live in today. It remains a source of inspiration for scientists and mathematicians alike, a reminder of the power of human ingenuity to unlock the secrets of nature. The echoes of Fourier's intellectual symphony still resonate, a timeless melody in the grand orchestra of scientific discovery.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.